Principles of Operating Systems, Chapter 3. Dividing an operating system into separate modules that can be loaded independently provides a great deal of flexibility in the way that the operating system can be dealt with in runtime. The alternative is to reboot with a new operating system image anytime you need to change the functionality, add new functionality to your system. Separating your operating system into distinct modules, each with specific responsibilities, makes it easier to upgrade the operating system capabilities when needed. Dynamically loadable modules provide a much simpler option than trying to build all conceivable functionality into the same operating system image. Loading on an as-needed basis helps keep the size of the kernel down. It reduces the system footprint and doesn't require that modules that you're not going to need occupy space in RAM. This is, of course, particularly important for systems with limited resources, in particular like embedded devices. And since you don't need the unneeded modules, it keeps the random access memory requirements down and allows your systems to operate at a lower price. Operating systems have to do lots of different things. It's only reasonable to separate out the functions into specialized subprograms or modules. Now, some of the modules have to have code that would have to be in memory and RAM at all times, but other parts of the system don't have to be used that frequently and can be loaded dynamically as needed, allowing the system to operate in a reduced footprint and use less expensive, more efficient systems. This type of organization simplifies the design of what is, by nature, an extremely complex type of program. It also makes it easier to update an operating system, something that happens with some frequency. Then this way, an update would only involve modifying a small part of the program, one or maybe two modules at any given time. Among the subdivisions or module types that an operating system will typically use, they would have a process management module, a memory management module, and modules for input-output. The process management module controls which processes are allocated to processors for execution. The process management module includes processes or programs that switch processors from one process to another. That is, they transfer processor control from one process to another process. A process is an entity that can be assigned to and executed by a processor. It's a unit of activity with a sequence of execution, a state, and a set of resources. It has three components: code, data, and context. When the processor starts executing code, that code has to be associated with a process. The process involves an identifier, a state of the process, a priority for the process, a value for a program counter, memory pointers, context data, input-output status information, and accounting information. There's a process control block, PCB, that contains those elements that we mentioned: identifier, state, priority, program counter, memory pointers, context data, I/O status, and the information necessary for keeping track and accounting. It's this PCB that makes it possible to interrupt a running program, process, and resume execution later as if there had been no interruption, that it simply continued. The PCB is created and managed by, guess what? The operating system. The PCB is a key tool. It allows support for interrupt processing and for multiple concurrent processes, multiprogramming. One of the basic activities of a process manager is to remove a running process from the CPU and transfer control to another process so the CPU can continue processing different processes. Now, of course, there has to be a reason for choosing one over another. This selection process has to be made on the basis of some strategy. Process scheduling is an essential part of multi-programming operating systems. The operating system keeps all of the PCBs in process scheduling queues. The system keeps separate queues for each process state, and the PCB of any process in the same execution state is placed in the same queue. When a state of a process is changed, then its PCB is unlinked, removed from the current queue, and linked into a new queue, the queue for the new state. There are several different state models. The simplest is the two-state model. which has only two states, running and not running. In this kind of a system, a process is only created if it can start executing immediately. They're only entered into the system when they can enter as running processes. In the system, then, when a running process gets interrupted, then it transferred into the not running queue, unless it's finished or it's aborted, in which case, either case, that process disappears, or otherwise it gets transferred into the not running queue. And another process is chosen from the not running queue to start executing. The five-state model is probably the most commonly used. In the five-state process, you've got 5 states: created or new, ready, running, blocked, and exit. Created, this is when the process is first loaded into RAM, but has not been entered into the waiting queue for execution, or the blocked process. In other words, it's entered but not in an executable state. It's waiting for the system to identify what to do with it. Ready, in the ready queue, would be our processes that are ready to execute, just waiting to be assigned a processor, ready to go, can execute at any time. Running is a state in which the process is actually being executed. Blocked, it's waiting for some event to happen, like in I/O completion, like some resource to be allocated, something. And then there is exit, when the process has finished executing, it's moved into the exit queue before being terminated, removed from the system. In systems that support virtual memory, there are 2 additional process states available. States where the processes are stored in secondary memory. Swapped out waiting, swapped out blocked. Suspended and waiting means it's ready to go, but the code that the process has been swapped out to secondary storage. Swapped out and blocked, it has been blocked, waiting for I/O or some other resource, and not being needed, not being ready to run. It has been swapped out to secondary storage until such time as it might be ready to go. There are lots of reasons that a running process might stop. Might have finished its time allotted, might have stopped to wait for an input-output operation to complete, might have stopped to spawn a new process, might have just finished, might have been preempted by a higher priority process, might have got to a point where it needs some other new system resource, or some other reasons. Whatever reason, if a process that's running stops, then something else has to start. Control has to transfer to another process. A CPU cannot just stop operating. When it finishes one instruction, it has to start another instruction. Control has to transfer to something. When a process stops, there's going to be an interrupt involved, possibly externally generated, possibly generated by the process itself, in particular, possibly signaling that it wants an input-output operation, possibly signaling that the task is finished. Whatever, the interrupt will include information needed for the system to determine what it is that should be done next. The process or program that takes up execution when an interrupt occurs is called the system monitor. Based on what kind of interrupt, the monitor will choose another process and set the processor to executing that process. When a running process stops because its time slice expires, then the monitor chooses a process, then that changes the state of the running process to waiting, put the now waiting process into the waiting queue, choose another process from the waiting queue, change the state of that process from waiting to running, and transfer control to that process so that it begins to run. If the process stops because it requests I/O, then the monitor changes the state of that process from running to blocked, moves that process into the blocked process queue, starts the appropriate I/O process to deal with that particular kind of I/O. The actual operation, input-output process is done by external equipment for that particular kind of input-output operation. And it's done directly by the external equipment, not by the CPU. Since input-output operations are slow compared to CPU operations, controlling them directly by the CPU would slow the computer down unacceptably. The process from the I/O module then starts the I/O equipment, starts it running, and then returns control to the monitor. The monitor then selects a process from the waiting queue, sets its state to running, and transfers control to that. When a process finishes its task, then it's going to issue an interrupt, the process termination interrupt. The kernel, the monitor, then initiates the process termination process from the process management module. What the process termination process does is reclaims the resources that the terminated process has assigned, then returns control to the monitor, and the monitor then selects a process from the waiting queue to start executing.